Good evening, everyone. Welcome to the 11th problem solving session of the course Computational Continuum Mechanics. As you know, I'm Naresh, a research scholar in the Department of Civil Engineering at the Indian Institute of Science. So the topic for today will be discretization of the virtual work equations. So this will be the second last session in this series. I hope it was useful for you, and the next session will be the last before your exam. Therefore, if you have any specific queries or any specific things that has to be clarified, you can tell me. I'll I'll do it in the next session. Okay, so let's get into the content for today. So to have a quick recap of what led us to discretization, we started off with seems to be a problem with my writing device. Yeah, sorry, there is some issue with my writing device. It's malfunctioning. Let me manage somehow. So we started with the equations of equilibrium last time, and it was the divergence of sigma plus the body force per unit mass per unit volume is equal to 0. This was the balance of linear momentum, and we have also had the balance of angular momentum, which was sigma is equal to sigma transpose. Now from here we said this is equivalent to the principle of virtual work in a sense that so the virtual work done by the internal forces on the internal strains caused due to an admissible virtual velocity field is equal to the virtual work of the external forces on the same admissible virtual velocity field. So in this expression, we saw that the internal virtual work done is given by integrated over the entire volume. So in Eulerian terms, we said it is sigma inner producted with the virtual rate of deformation tensor integrated over the entire volume. Right, this was the internal virtual work done, and the external virtual work done is what we would expect. It is the virtual work done by the external body forces. So it is F dot the virtual velocity field integrated over the volume plus the work done by the tractions. So F is a vector, del V is a vector. Here sigma is a tensor, del D is a tensor. It's a symmetric part of the gradient of this virtual velocity field del V. And here traction is a force per unit area. This dot producted with the virtual velocity field integrated over the surface. So this is a surface integral. Right? So this is a surface integral. Just a minute. So ultimately, the equation that we have to solve for is this, right? So the virtual external work done is equal to the virtual internal work done for all admissible virtual velocity fields del V. What is the next step? The next step in the last week, we did what is called linearization. So we linearized the virtual work done. Sorry. So we did what is called linearization. And for linearization, what did we do? We started with the expression for virtual work. So this is the expression. Let us call this as del W. This is equal to del W internal minus del W internal minus del W external. And this has to be equal to 0. So our configuration is given by this mapping. Suppose our solution is given by the mapping x is equal to phi of x comma t. Suppose this is the solution. The configuration is given by this mapping, the deformation mapping phi of x comma t. Then del W del W is the virtual work done associated with the current configuration, the stresses and the forces in the current configuration on an admissible virtual velocity field del V. So this takes in two arguments. This del W takes in two arguments. First one is the configuration itself, phi. And the other argument is the virtual velocity field against which we are testing it. So this has to be 0 if phi is the correct solution. But if we have a guess, or a trial solution, so if you have a guess or a trial solution phi k, then this del W of phi k comma del V, where del V is any admissible virtual velocity field, this will not be equal to 0. This will not be equal to 0. And this is nothing but the residual. So this is a residual. This is a residual, right? So this is just like how we solve f internal is equal to f external and we get a residual. This is similar, but this is a scalar residual. So one last. Okay, so it looks like you have to manage it this way. Fine. So suppose the actual solution is some phi, and that can be given as the guess plus a correction. Plus a correction, a displacement u. So this is the solution configuration phi. Phi k is the guess that we have taken, a trial, and u is the displacement. U is a displacement which corrects the guess to the correct solution. So in this case, we can linearize the virtual work equation. So what we actually want to solve is del W of P comma del V should be equal to 0 for all admissible virtual velocity fields del V. Now, this phi itself is pk plus u. So this is pk plus u comma del v equal to 0. So now you can this can be linearized. So this you can expand it as del w of phi k comma del v plus the directional derivative of the virtual work d del w of phi k comma. So the perturbation you're making is u. Therefore, this is the directional derivative of the net virtual work done at this point phi k comma del v in the direction u. Give me a minute. So this has to be equal to 0. Now suppose, look at this term. This is the linearization of the net virtual work done in the direction u. So this can be written as d del w. It has got two parts. One is the internal virtual work done at this point, p comma del v. So now I'm just using it as a phi is just the argument. It is not this point phi k. So I'm finding an expression for del w internal in the direction u minus the linearization of the directional derivative of the external virtual work done of p comma del v in the direction u. This should be equal to 0. And in the last session, we derived an expression for the internal virtual work done, what it is. So in the Lagrangian form, this case is better I use. Yeah, so the Lagrangian linearized virtual work expression is as follows. So it is uh, so let me write it down. So the linearization of this in the direction u, where u is the corrective displacement, is given by it has got two parts. One, the first part is integrated over the volume. It is the directional derivative of the green Lagrange train tensor in the direction of the virtual velocity field dot producted with um, the material, the Lagrangian constitutivity tensor, right? So this is a Lagrangian material constitutivity tensor, which is defined as ds is equal to c times de, where E and S are the green Lagrange train tensors and the second Piola-Kirchhoff stress tensors respectively. And this, so this is a fourth order material constitutivity tensor, d e u db. Sorry. So this is one term, and we also have another term coming from the stress, right? So the next term is coming from the stress. Plus integrated over the volume. We have the second Piola-Kirchhoff stress tensor acting on this product of two gradients. So what is the gradient? One is del with respect to the reference configuration of u. This one transposed del v. dV. So this was the expression for the linearized virtual work in Lagrangian description. Right? So this is this. The first part is a constitutivity part. So this is so this. So this is constitutivity part. So let us call it C, and this is the stress part. So the next step is we obtain the same thing in Eulerian. So this was the Eulerian linearization of virtual work. So this, if you recall, we obtained it just by pushing forward the expression we got in the previous step. So this is nothing but increased size. So again, I don't have to write it again. I'll copy paste this. So this is equal to. This has also got two parts. One is the stress part. So in this case, the stress part is the virtual rate of deformation tensor multiplied with the Eulerian, the spatial elasticity tensor, the spatial constitutivity, or the spatial elasticity tensor, dot producted with the infinitesimal strain tensor epsilon. And this is integrated over the volume. But here it is the deformed volume. So let me use a small, or this is a deformed volume. And this has got the second part, which is coming from the Cauchy stress instead of the second Piola-Kirchhoff stress. So this is the Cauchy stress contracted with the gradient of the displacement and the product. So this is the same, except that the gradients are with respect to the current configuration or the original configuration. So here it is. dV. Right, so this is the expression for the linearization of the virtual work in the Eulerian description. So okay, this is del V. This is the virtual velocity field, so it's del V. So one thing to be noted is that both the Lagrangian and Eulerian descriptions of the linearized virtual work, they are symmetric in the virtual velocity field and the direction of linearization, which is u. So it has got to be symmetric because by definition, it is a directional derivative in the direction u. Therefore, it has to be linear in u. In addition, wherever we started off with, that is linear. The virtual velocity, the virtual work expression itself is linear in del V. So the linearizations of the virtual work have to be linear and symmetric. It should be bilinear in each of its arguments, u and del V, and it is symmetric with respect to u and del V. So that's an important observation. I hope this works. So it is always easier to. So both of these procedures will end up in the same discretized equations, but usually it is easier to work with the Eulerian description. So this is easier to work with. So this is this when we follow this results in something called the total Lagrangian formulation. When we follow this, this results in a Eulerian or updated Lagrangian formulation. So this is what we'll be pursuing, and it is easier to work with the Eulerian linearized virtual work. Now here so these are still continuous quantities. This is all admissible virtual velocity fields. They are infinite in number. This is all possible configurations, and this is some U is a continuous field. So these are all infinite dimensional, and we cannot solve infinite dimensional problems on a computer. So we discretize it. So the next step is discretize. Yeah. So the next step is discretize. So by discretizing, we are converting this infinite dimensional problem into a finite dimensional one that can be solved on a computer. So how do we discretize? So this, as you might have covered, as you might have seen in the lecture, we start with the discretization of the geometry. So the undeformed coordinates, these define the geometry of the body. So so first we have to discretize. So by discretizing, we mean that we express the solution in as a linear combination of a finite number of basis vectors. So it's like expressing in a finite basis. Expressing what in a finite basis, that we'll see. Expressing in a finite basis. Right. So the first thing that we have to discretize is the geometry. So geometry is given by the reference coordinate system x vector, and this can be discretized as follows. So you locate. So there are infinitely many points in the reference configuration, but we cannot track all of them. So you track certain points called nodes, and these nodes are supposed to identify a node by this subscript a, and these nodes and these suppose these nodes have a, so let me put it this way. So we have a reference body, and that reference body has got a large number of particles. We cannot track all the particles because we cannot deal with infinite number of particles. Therefore, we identify certain points of interest called nodes. So these pink points are called nodes, right? And in between the nodes, we interpolate the geometry. So for example, if I want to represent a function, if I want to represent a curve like this, I select certain points on the curve, and everywhere in between I linearly, or I interpolate, right? I interpolate everywhere in between. So the interpolation defines the discretized geometry. So instead of handling infinitely many points, we handle a finite number of points. Therefore, interpolation, as we know, it is given as the product of the known values, let us call it xp, and producted with the interpolation functions. So in finite elements or in computational mechanics, we call them shape functions. So P is the node index. It goes from 1 to the total number of nodes. Let us call the total number of nodes n. And NP is a function of some referential parameters. And these referential parameters are usually called xi. So in 3 dimensions, we need 3 referential parameters, xi1, xi2, and xi3. Right? So this is how we discretize the given geometry, right? So we start with a this is the continuous set of all points, but we cannot track all the points. So we look at the node points, which are identified by the index p. In between the nodes, we use some interpolation, and these are called the shape functions. These are called the shape functions. And these are defined on a parametric coordinate system. And what is the parametric coordinate system? That is our choice. So we can choose the parent coordinate system to our interest. So for example, we can so we if so we can deal with a Euclidean set of coordinate axes, say This could be xi1 axis, xi2 axis, and xi3 axis. And we can consider a unit cube, a bi-unit cube. And map it to any cube in the so for example, this, if suppose this is the geometry, is yes, Aman, you
Yeah. Please continue. Yeah.
okay, yeah. So you can always map it to a cube, to a deformed cube in the current geometry, right? So you can have curved walls, and this mapping is brought about by the shape functions n. Now, so given this, so this is the idea. So this is used. So this mapping is called an isoparametric mapping, and this forms the fundamentals of all basis finite elements. Now, given this, we have already discretized the geometry. The next step is to discretize um, the solution itself, right? So we can always we can also do the same thing. So you track the node points, you track their positions as they convect to the deformed body. Suppose this is a deformed body. These nodes are going to move to other points. So say they move to some other points. And suppose their current positions are denoted by the capital letter, small letter x. Right. So this mapping, again, the current positions can also be interpolated. So consider a parametric region bounded by xi1, xi2, xi3. And we can track the current locations of these node points. And for the points that are lying in between, we can use the shape functions to interpolate. Again, you track the current locations of the node points, xp. And for everywhere in between, use the shape functions, np of xi1, xi2, and xi3. Again, a p goes from 1 to the total number of nodes. And so yeah, so today, since my writing device is not working, I'm finding it hard to write. So let me start solving the problems directly, right? I have prepared for reviewing the entire lecture, but unfortunately, this is causing some issues. So let us start solving this problem. It's better. So here's an example of a two-dimensional.
Naresh,
Yes,
I have one doubt. Please,
yes,
can I ask? Okay. Okay.
sure, yes, tell.
Naresh, last year there was one course on NPTEL. I did that, and the
Okay,
name was Variational Methods to Computer Programming. Okay,
okay,
and just same thing that you are elaborating today.
okay.
I did in a separate way there.
Oh,
Also,
okay,
I did. Okay.
okay.
Actually, I want to know,
Uh,
just please tell me this F, that is deformation gradient tensor.
yeah,
So this deformation gradient tensor just tells about the relationship between the two coordinate system, or some distorted geometry to the parent or material geometry, or what it tells means why I'm asking, because Jacobian is included in that matrix.
okay, yeah. So that's a good question. So what you have is deformation gradient has the complete information about the entire deformation. So it's like,
Okay.
suppose we have a body, right?
Mm-hmm.
You have a body at time t is equal to 0. Let us call it b0, and you have
Mm-hmm.
some other body. Say this body takes up this shape, right? So at every
Mm-hmm.
point you have a deformation gradient. What it means is that, so you have one mapping which is phi. which says the motion of all the points in this as a function of time. So this can be the body at time t. But this this motion itself is in some functional form. So you'll have some phi1 of say x1. Okay, thank God. I think it started working. Let me just check this writing device.
Okay.
Oh yeah, great. It started working. Yeah, let me. This is such a relief. I have been struggling. Okay. So this is so you start with say x1 is equal to phi1 of x1 comma x2 comma x3 comma t. X2 is equal to phi2 of and so on. Similarly, x3 is something. So if you look at it from classical physics point of view, every body is a collection of many particles. So if you know where every particle is going at time t, you know the deformation. It's not really deformation. You know the motion of the entire body. But dealing with the motion itself is not going to help us with computing internal forces, right? So internal forces are generated due to relative motion between particles, and we are precisely interested in that information. So what we are more interested in is how adjacent particles are deforming. So you take two particles in the undeformed body, let us call it B, and let us see where these two are going in the deformed body. So say they go to some, yeah, they go to some other points, x1 and x2. So anything that has got to do with internal forces, stresses, and strains have to look at relative displacement between these two particles. Suppose this vector is given by d capital X. Now we are interested in seeing how are they moving apart, are they moving close to each other, and things like that, right? So we know this x1 is equal to some phi. So this is the vector x1, right? This is the point x1. This is the phi of x comma t, x1 comma t, and this x2 is phi of x2 comma t. So now we are interested in how these two are moving. So we want to look at this vector, the vector connecting x1 and x2 in the deformed configuration. So this is phi of x2 comma t minus phi of x1 comma t. But what really helps us here is if we take these 2 points are infinitesimally close, this x2 is nothing but x1 plus dx, right? So this
Yeah.
at this point you come to substitute here. So you see x2 minus x1 is equal to phi of x1 plus dx comma t minus phi of x comma t. Now this you can expand it in a Taylor series. So the first term will be gradient of phi dx at the time t, plus you have higher order terms, and the higher order terms will be of this form: dou phi by dou square phi by dou xi dou xj dxi dxj, and you have something 1 by 2 factor or whatever, and so on, and you'll have higher order terms. Now if these points are sufficiently close enough, this will be dominated by this term, so you can drop these, and this is precisely the deformation gradient f. So when you take 2 points that are sufficiently close enough, in the deformed configuration, they might move apart, they might come closer, they might rotate rigidly. And each of this is a different local deformation, right? So locally, you can have different kinds of deformation, and this is entirely characterized by f. So where f is the gradient of. So that is it's like, so the deformation gradient is something like velocity vector in physics. So or velocity in flow fields, right? So you uh, in when you analyze flows, you're at with as a function of time. At every instant, you are looking at, if you look at a particle at that instant, at that location, you see how the velocity field is, and that gives you the complete information required for the further problem solution, right? Similarly, in mechanics, in solid mechanics, uh, uh, you can have a motion, but locally, everything that affects the response of the material is whether particles are moving apart or they're coming closer. And that entire information is handled by this gradient, and this itself is a function of the point and time. So this that is the significance of the deformation gradient. And it turns out that this is nothing but dou phi I by dou xj, and it is a tensor.
Okay.
Yeah, this is the
So means
Jacobian. Yes.
okay. So means we can say it contains the deformation data as well as the shifting of individual particles. If even the distance between the particles are same in both the configuration.
Yes, yes. So,
Okay.
for example, if you consider rigid motion, right? So you can say rigid motion is x is equal to x plus
Mm-hmm.
some constant. Say, let's even make it a function of time, c of t, right? If you consider
Mm-hmm.
rigid motion like this, what should happen? We should not have any gradient because adjacent
Yeah.
particles are not moving apart,
Yes.
right? So,
Moving apart. Yes.
so this, if you see, um, so if you look at the okay, so let me see this. X is equal to x plus c of t, right? So now you compute the deformation gradient. It turns out to be, so this is defined as x1 is equal to capital X1 plus c1 of t. Uh, x2 is equal to x2 plus c2 of t. x3 is equal to x3 plus c3 of t.
C3T.
Now, what does it mean? So now, if we compute the deformation gradient tensor, it is first one derivative with respect to x1, x2, x3. So it will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Note that c does not depend on the x. So what it
Mm-hmm.
means that if you take 2 points initially apart by a vector dx,
Mm-hmm.
even after deformation, those points will remain as it is. And that is the definition of rigid motion, right? So this is what it means. So this you can clearly see the vector neither gets rotated nor
Mm-hmm.
it stretches or contracts. So it remains identity. So so the relation is dx d small x is equal to f d capital X. And you see if you take a vector d capital X after the body moves, so the c of t can be very big. This doesn't mean there's infinitesimal deformation or anything. This can be
Mm-hmm.
100 meters or whatever. But what it
Mm-hmm.
says is if you take two particles apart connected by a certain vector, after deformation you recover the same vector. So vectors are equal means both the magnitude and the direction are equal. So the line connecting these two has not even rotated. So
Mm-hmm.
this can be captured. Similarly, if you have a rigid rotation, right, you can also look at that. You can have a rigid rotation field. So it's like you can think of it as, so suppose you have a body like this, and the body is kind of yeah. So suppose so it's and one more thing is it is independent of coordinate system. We use a coordinate to represent it. Say the body undergoes a rigid rotation, right? So
Mm-hmm.
rigid rotation, you can say if you take vectors like this, it becomes this. And the
Mm-hmm.
relationship between these two, it is given by. So suppose let me take planar case, right? Let's just take planar, and let us say, uh, let us look at this field. It is rotating as well as moving. Let us say x1 is equal to cos theta x1. Suppose it rotated by theta plus sine theta x2 plus c1 of t. And this cos
Mm-hmm.
theta can itself be a function of time, right? So let me put that. And x2 is minus sine theta x1 plus cos theta x2 plus c2 of t, right? So
Mm-hmm.
this is a rigid rotation, rigid motion. So this particle has translated by c of t, and it is also rotated by some theta. Now let us compute the deformation gradient for this. So this will give us uh, cos theta of t, sine theta of t, minus sine theta of t, cos theta of t. Right. So this is the deformation gradient as a function of this thing. Now, is this now what this says? This means that if you take two particles separated by a vector dx, after deformation it becomes something else. It becomes some f dx. But let us see what that f dx is. Now uh, from this f you can compute the uh, right Cauchy-Green tensor. So
Mm-hmm.
this is given as
FFT.
f transpose.
Mm.
Yeah, f
FFT.
transpose f.
FFTs.
No, that is
Okay, okay.
b. B
Oh,
is
yeah,
f
that is
f
big. Yeah,
transpose.
yeah, yeah, yeah,
Yeah.
yeah.
So from this, you can take any measure. You can either work with this. So if you take this, this will be cos theta minus sin theta, cos theta, acting on
Yeah.
cos theta, sin theta, minus sin theta, cos
Minus
theta.
sin theta cos theta. Yeah.
So the first one will give cos square theta plus sin square theta 1. Second, this
Yeah.
will be 0, cos theta minus sin theta. This will also be 0 because it is symmetric, and here it is 1. Now,
Mm.
what does this mean? So now you compute any measure of strain. So because we have defined the motion to be a rigid motion, we have designed it as a rigid motion. Now you take the green Lagrange strain. It is what? It is half of C minus identity. C itself is
Yes.
identity. So this is
Yeah.
0. So
Yeah.
this deformation gradient has the entire information to capture rigid rotations as well. And now you can also take it for any arbitrary shear, right? Simple shear you would have seen in the. So suppose you have a body like this, or let us take yeah. So just take the body as a square, and after deformation, say it has become big, like it has expanded in a proportional manner. So what happens if you use similarity of triangles? You can say if this is capital X1 and it has expanded to some alpha X1. So if it is expanding uniformly, you say X1 is equal to alpha X1, X2 is equal to some alpha X2. Right? In this case, the deformation gradient tensor will be just alpha alpha 0 0. And now if you see what is C, it will be nothing but alpha square alpha square. And you see what the green Lagrange strain tensor is. It is alpha square minus 1 by 2, 0, 0, alpha square minus 1 by 2. Now what it says is you are having only E11 and E22.
Mm.
And there is no shear.
Yeah.
So again, the starting point is always the deformation gradient tensor. So given any point, or if you have a homogeneous deformation, so close to a point, the deformation is always homogeneous. Homogeneous, I mean, f is not a function of x. So homogeneous deformation means all the points have the same deformation gradient tensor. And if you zoom in sufficiently close to a point, deformation is always homogeneous. So at that point, you can always describe everything that is going on locally by means of 9 components of the deformation gradient tensor. So that's why it is such a powerful concept in mechanics.
Okay, and when we get this type of coefficient matrix in F, I
Yeah,
think the we can say that it's just like something like hydrostatic compression or tension or something like that.
this one, you
Yeah,
mean
alpha
this?
zero zero alpha,
Yeah,
alpha
yeah.
zero zero
Whenever you
alpha.
have a tensor like this is called a hydrostatic or a spherical tensor. It's called
Okay.
hydrostatic or a spherical tensor. But you can't call it hydrostatic compression or something because that is to do with the stresses. So stresses of the form lambda I, then it is hydrostatic this. But in general, when F is a diagonal, that doesn't mean anything. It means that, yeah, it is, you can think of it as, you can call it spherical. You can call it spherical, but yeah, hydrostatic is reserved usually for the stresses.
Can we say this? Can we say this as the homogeneous deformation?
Yeah, this is homogeneous because this does not depend on X. You can also
Yeah,
construct
yeah, yeah.
non-homogeneous deformations. For example, if you take, yeah, that's an interesting problem. Suppose you take a, mm, yeah, this was my exam problem here. So suppose you take a straight line like this. You take this region,
Mhm.
or rather, just take, yeah, you take this region, and suppose it becomes a semicircle, right? So now you can construct, so this whatever triangle is there, that is becoming a quarter of a circle. Now again, and suppose the deformation is such that it moves along this line. Every point on this in this triangle exterior moves radially outwards. Right? Suppose this is the thing. Now you can construct this similar triangles, right? So you see every point. So this, suppose this is to make it simple. Let us say it is 0 1 uh, triangle, and this is the semicircle connecting the same 2 points. So this, every point on this triangle is of what form? It is of the form x plus y is equal to 0.
Mm,
Sorry, x plus
mm,
y is equal to 1. So uh, so every point will be of the form x comma 1 minus x. And on
mm.
the circle, what will be the form? It will be of the form some r cos.
under root yeah,
Yeah,
r cos
yeah,
theta r sin theta.
yeah. So r in this case is 1, right? So you can call it
Okay.
as cos theta comma sin theta.
Yeah. Yeah.
Now, but what is theta? So theta is this angle, right? So theta is nothing but y by x.
Hmm.
Tan theta is y by
Tan
x.
in. Yeah.
Yeah, tan theta is y by x. So the what is the mapping here? So uh, so the original bodies of this form x1 comma x2, new bodies of the form x1 comma x2. What is x1? X1 is cos theta. But what is theta? Theta is this thing. So cos of tan
Tan
inverse
inverse
of
y
y
by
by x.
x.
But yeah, you can take it as x2 by x1.
X. Yeah.
And x small x2 is sine of tan inverse of x2
X2
by
by
x1.
x1.
Now, so this is the mapping. This is the mapping. Now you can go ahead and find out the deformation. So this if you simplify this further, cos will be what? It will be x1 by square root of x1 square plus x2 square, and this will be x2 by square root of x1 square by x1 square plus x2 square. Now you can find the deformation gradient tensor for this. So if you see what is f11, f11 is dou by dou x1 of x1 by square root of x1 square plus x2 square. So do this differentiation, keep the denominator as it is. So in the first term, you have 1 by square root of x1 square plus x2 square plus x. Then differentiate the second term, you get minus 2 x1 square plus x2 square the whole cube, and differentiate whatever is inside it. So I get 2x1.
Yeah.
So simplify this. Yeah, we can't say 2, only 2 gets cancelled. So this is what it is. So it is x1 square plus x2 square minus x1 square divided by x1 square plus x2 square the whole power 3 by 2. So this is nothing but x2 square by x1 square plus x2 square the whole power 3 by 2.
3
Now
by 2.
this similarly you can find f12, f22 and so on. So yeah, you can do that. But what you see is that f11 itself is a function of x1 and x2. So
Yeah.
the deformation, if you so what it physically what it means is you take the neighborhood of one point which is x1 and you take a neighborhood of another point x2. Here the way two adjacent points are deforming is different from how two adjacent points are deforming here. That's what it means. So locally deformation is homogeneous, but if you take 2 points that are farther away, the way the local deformation here is different from the local deformation here. So straight lines do not remain straight lines. Therefore, it is a non-homogeneous deformation.
Yeah.
That's okay, right? Anything else?
No, no, no. You can proceed.
Okay, okay, okay. Anyway, I'm happy that this device started working, writing device. Okay, so let's get started. So this what I was talking about is interpolation, and we said the first thing is geometry, and geometry can be interpolated using the shape functions as x is equal to summation over all the nodes, the location of the nodes xp, and uh, uh, multiplied by the shape functions na of xi1, xi2, and xi3. Now we are given this problem, right? So the we are suppose we start with this. So yeah, so now you can follow carefully. Now I'm defining the parent coordinate system, the parent body. Let me say parent body as follows. So the parent coordinate system xi1, xi2, xi3 is just a parameterization of the geometry. I can choose it as I want. So what I'm choosing is, because of similarity, let me take it as let me take it similar to this. So let me take the parent element as a triangle. So it is This is the origin 0, 0. This is 1, 0. This is 0, 1. So this is my parent element, and this is in the xi1, xi2 coordinate system. So this is in the xi1, xi2 coordinate system, and I am defining the parent element as this. Now, the first thing I'm going to all my interpolation functions will be defined in this. All my interpolation functions are defined in the parent element. You can say element. So so what I'll have is I'll have n1 of xi1, xi2, xi3, and so on up to n3 of xi1, xi2, xi3. So why? Because we have in this problem we have three nodes. This is node 1, this is node 2, this is node 3. And after deformation, it goes to node 1, node 2, and node 3. Now let us look at the so in real problems, in computational problems, nobody will give us a mapping like this. Nobody will give us x of x comma t. No, this will not be available. This will be what we solve for, right? This will be what we solve for. And even if it is given for implementation in a computer, we'll be given only the motion of a finite number of motion of a finite set of points. And these are called nodes. And in this case, we are given three nodes. So for the deformation everywhere in between, we have to do interpolation. Okay, so that's the case. Now let us do interpolation. Let's do interpolation. For first, the task is to interpolate the geometry, and let us call these nodes oriented similarly. Let us say this is node 1, node 2, and node 3. Now, what is x of x1 is equal to 0, 0, 0. X2 is equal to 4, 0. And x3 is equal to 0, 0, 3. 0, 3, 0. So this is our mapping. Sorry, this is our parent. This is our geometry. This defines our geometry. But what is this a function of? This is a function of xi1, xi2, xi3. So when so what the details that we have is we have a certain mapping, and when we have xi1 equal to 0, xi2 equal to 0, xi3 equal to 0, this goes to node 1, which is x1. And when we have xi1 equal to 1, xi2 is equal to 0, and xi3 is equal to 0, this goes to x2. And then we have xi1 equal to 0, xi2 equal to 1, and xi3 equal to 0. This goes to the point x3. Now, first thing is we have to construct the interpolation functions in the xi1, xi2 domain. So how do we go about the interpolation functions?
Using for example, we are considering the node 2 here. So
Okay.
we have to choose the interpolation function such that the value with respect to node 1 should be 1, and of the node 2 and 3 should be 0.
Yeah, perfect. So that's exactly how we do it. So here at this point, it should be, for example, the second interpolation function at 1, 0 should be 1, and at other nodes it should be 0.
Yeah.
So this is fine. First, so let's ignore the third coordinate for a while. And what we have is we have 3 points, which means we have 3 unknowns. So we can start with a linear interpolation function. You can look at it something like n of xi1, xi2 as some a0 plus a1 xi1 plus a2
A2
xi2.
xi2. Yes.
Now what we have is so the interpolation functions are such that you okay, so So this is the general form of interpolation functions. Let me put an A here. So for all three nodes, the interpolation functions are like this. Now suppose I have a polynomial. Let's do one thing. There are easier ways to do it. Let me or let's just do brute force, right? Let's just do some guessing work. So what is this line? This line is xi1 equal to 0, and this line is xi2 equal to 0. Now at any two, so on xi1 equal to 0, we want, so on xi1 equal to 0, we have these two nodes, right? And at these two nodes, what should be 0? N2 should be 0. So on xi1 equal to 0, we want N2 should be equal to 0. And similarly on xi2 equal to 0, we want N3 equal to 0. So basically what it means is N2 of xi1 equal to 0, comma xi2. For all xi2, this has to be 0. And for N3, it is xi1, comma xi2 equal to 0, equal to 0. Right? When xi2 is equal to 0, N3 should be identically 0. And when xi1 equal to 0, and N2 should be 0. So let us just start with this, right? So let us try N2 of xi1, comma xi2 is just xi1. Right? So when xi1 is equal to 0 on these two nodes, it will be 0. And at this node, it will be 1. So this function satisfies that. And similarly, N3 of xi1, xi2 is equal to xi2. So this is one way we can choose this, right? So this is linear. So this satisfies these properties. So you are trying to interpolate between this, right? So on nodes 1 and 2, what vanishes? N3 vanishes. And on nodes 1 and 3, N2 vanishes. Now we also need one more interpolation function for the node 1. Now we'll see how to choose that. So our idea is we are expanding x as summation NA XA. Right? We are expanding in this form. Now if I substitute, so just take any point. So let us just take any point. Now x is equal to, we already have two of the shape functions. So one is xi1 times x1 plus, sorry. Xi1 times xi1 is x3. So xi1 is, no, sorry, x2. So it is xi1 times x2 plus xi2 times x3 plus you have some other function n1 of xi1 comma xi2 times x1. And this is any point. This is the interpolation for any point. Now, now what is the value? Now what do we want? When xi1 equal to xi2 equal to 0, we have x equal to x1. Right? So what it means, n1 of 0 comma 0 should be 1. Then when we have xi1 equal to 1 or xi2 equal to 1, we want, so when we have xi1 equal to 1, we want x of 1 comma 0 should be equal to x2 and x of 0 comma 1 should be x3. This is the mapping we have, right? So when xi1 is equal to 1, what will happen when xi1 is equal to 1 and xi2 equal to 0, this will not contribute. So we get, so this basically means n1 of 1 comma 0 should be equal to 0 and n2 of 1 comma 0 should be equal to 0. Sorry, 0, n2 of 0 comma 1 should be equal to, sorry, n1 of 1 comma 0 should be 0 and n1 of 0 comma 1 should also be 0. So what I have done is I have just substituted xi1, xi2 corresponding coordinates here, and these results in these equations. But we already have some conditions here. Substitute them. So when xi1 is 0, this will not contribute. You will get x3, but you should not. So when you put 0 comma 1 in this, 0 comma 1 corresponds to x3. But which means this has to be 0. It should not depend on x1, so this has to be 0. So n1 of 0 comma 1 should be 0. Similarly, when you substitute 1 comma 0, we'll have to get x2 identically, which means this is anyway 0 because xi2 is 0, and n1 of 1 comma 0 should also be 0. So these are the two conditions. And when will this happen? This happens when look at any point. So you just take any point, and we saw it is linear. So this, the only linear function that vanishes at both. So we want a linear function vanishing at 1 comma 0 and 0 comma 1. So what is that function? Let us say that function is a0 plus a1 xi1 plus a2 xi2. What we have is when we put 1 comma 0, it should be 0, and when it is 0 comma 1, it should be 1. So so we have three conditions. So a0 plus a1 into 1 plus a2 into 0 is equal to 0. a0 plus a1 into 1, a1 into 0 plus a2 into 1 should be equal to 0. And what is the other condition? N of 0 comma 0 should be 1 because it has to identically give x1, which means a0 plus a1 into 0 plus a2 into 0 should be 1. So can we solve for this? So this can be solved. The system can be solved. So we get a0 is equal to 1. The second equation tells a0 plus a2 is equal to 0, which means a2 is equal to -1. Similarly, a1 is equal to -1.
-1. Yeah.
Yeah. Therefore, the correct shape function n1 of xi1 comma xi2 is what? It is a0 plus a1 xi2 plus a2 xi2. It is 1 minus xi1 minus xi2. Now these are the shape functions. We got the shape functions. So the shape functions are, so the shape functions are, you can say it is for node 1, it is 1 minus xi1 minus xi2. For node 2, it is xi1, and for node 3, it is xi2. These are the shape functions. Now we can interpolate the geometry. X is equal to summation na, a going from 1 to 3, capital XA. What is capital XA? So capital X has got these coordinates. Right, so capital X is 0, 0, 4, 0, and 0, 3. So I can write this capital X as summation. So it can be written as, so first one, it is 1 minus xi1 minus xi2 multiplying the first coordinate, which is 0, 0, plus the second coordinate is xi1 times 4, 0 plus xi2 times 0, 3. This is the interpolation for geometry. Now you can see that if you substitute 0, 0, you will recover the first point. If you substitute 1, 0, you'll recover the second point. If you substitute 0, 1, you'll recover the third point. What is this? This is the geometry. The second thing that we have to interpolate is the current configuration. So next thing, let me just restart this. There is this PowerPoint issue, but okay, no problem. So next thing we have to do is current configuration. Now, what are the coordinates? It is 2, 3, 10, 3, and 10, 9. So we have x1 is 2, 3, x2 is 10, 3, and x3 is 10, 9. So note that it looks like it is rotated, but it is not, right? So point 1 is here. This angle has changed from 90 degrees to something very small. 2 has gone from acute angle to a right angle, and 3 has moved a lot. So this is not a rigid rotation or anything. So this has significantly deformed. Now same thing. So we use the same shape functions to interpolate the current configuration as well. So it's P going from 1 to 3, XP, NP. So NP is a scalar, XP is a vector. So you can write this as the current configuration is 1 minus Xi1 minus Xi2, 2, 3, plus Xi1 times 10, 3, plus Xi2 times 10, 9. Okay. Now let us compute the deformation gradient. What is the next step is compute the deformation gradient. So let us compute the I'm think I'll have to restart this.
So did you save that or not?
No, it will be auto saved, but some of it may be lost. But we can't do anything. That's yeah. Some of it is lost, but it's okay. I remember the expressions. Okay, let me reshare my screen. Yeah, it is saved only up to this point, but it's fine, no problem. Anyway, we know the interpolation functions for the. Okay, so this we have, sorry, capital XC, and we have small x also defined in a similar way. We are using the same interpolation scalar functions as a function of xi. Let me just put xi j and xa. And we saw that x1 is 10, what was it? 2, 3, 10, 3. Yeah, 2, 3, 10, 3, and 10, 9. So x1 is 2, 3, x2 is 10, 3, and x3 is 10, 9. And this is interpolated as shown. Now the next task is to find the deformation gradient. So let us find the deformation gradient. So we have, so let me just recall the concepts. X is equal to, usually we have X is equal to some phi of X comma T, and we call grad phi as the deformation gradient. In this case, we have X as X written as a summation, P going from 1 to N, here N is 3, XP, NP of some Xi j. Now, this grad, if you recall, is with respect to the original configuration. So what I want is, if I want the ijth component of the deformation gradient, it is dou xi by dou xj. But what is the independent variable here? The independent variable is xi j, not xj. So I have to use the chain rule. So I can write it as dou xi by dou xi p, dou xi p with respect to dou xj. Now, this dou is IP with respect to dou xj. Again, so this is fine. This we have directly because we have the shape functions defined over the parent coordinates. So these are the shape functions over the parent coordinates. And but what about this? How do xi vary with the current x? So here we have the assumption of invertibility of the map. So if it is invertible, this is the pjth component of, this is the pjth component of, pjth component of what? It is the pjth component of the mapping from the parent. So this is the parent coordinate to the undeformed body. This mapping is X. But you have an inverse mapping which takes in a point in the material body and finds out what is the corresponding point in the parent coordinate. And this mapping, as you know, it is X inverse, right? So if you ask me uh, what is this? This is the jpth component of X inverse. So so this product can be written as this is when we have this connection problem, this issue comes up. I have to save it. Save it. Okay, it is saved, no problem. Okay, so uh, this is dou xi by dou capital Xj, and this is dou xi by dou xi p, dou xi p with respect to dou xj, and dou xj with respect to dou xi p is the jpth component of grad.
Are you writing something?
Oh, is it not visible? Okay, okay. I think the screen share is. Let me share the. Yeah. So it is jpth component of uh, the gradient with respect to xi coordinates of x. Okay. So we have. So I was just writing this. So this you have a mapping from a parent xi domain to the undeformed body, which is x. And from the undeformed body, we have a mapping to the deformed body, which is the deformation. And this is given by the shape functions. Let us call this mapping x. This is the deformation. But this mapping, if it is invertible, so under certain conditions, this mapping is invertible. If it is invertible, we also have an inverse map, which is x inverse. So this xj with respect to p is jpth component of this gradient of this mapping. Now, now this is easy to find out. Why? Because we have x as summation a going from 1 to n, na xa, and the functional dependence on xi is only in na. Xa is a constant vector. Dou xj with respect to xi p will be summation a going from 1 to n. Dou na with respect to dou xi p xa, right? And what will be dou xi p with respect to it? So this will be a tensor. This will have 9 components as j goes from 1 to 3 and p goes from 1 to 3. This will be a component. This will be a matrix of 9 components. And this is exactly the inverse of that. So this is actually inverse of that. So therefore, what we have is Fij is equal to, the first one is very straightforward, dou xi by dou xi k, or whatever. I use p, I think, p. And here I have the inverse of a map, and that map is the gradient of x with respect to xi inverse. Which component? It is the jpth component. This is the jpth component. This is the jpth component of this inverse. But what is this? This is the gradient of the deformed body with respect to xi. This is the ipth component, and this is jpth component. Now this can be written as so this you can write it as transpose pjth component, and this will be xi x ipth component, right? So this and first index in common. So this is nothing but del x xi del this one. So this is a product of two tensors. So this will get contracted, right? This will get summed up in indicial notation. So this is the ijth component of. So there's a transpose here. This is the ijth component of this, and therefore f is equal to, now get rid of the component. So it is the gradient of the current configuration with respect to xi multiplied with the gradient of the reference configuration with respect to xi transpose inverse. So this is inverse. Sorry, there's an inverse somewhere, and this is inverse. So this is inverse. So this is inverse transpose. This is inverse transpose. So you have an inverse transpose. So this is the expression for the deformation gradient. Now substitute for x. So here the derivatives are only with respect to xi. The derivatives are not with respect to x. So this can be directly computed. What is the derivative? Again, okay. So so the first one, xi derivative of x is nothing but summation. So so it is derivative with respect to xi np of xi xp, right? P going from 1 to n. Summation doesn't depend on xi, xp doesn't depend on xi, so it's nothing but p going from 1 to n, gradient of np with respect to xi xp. So it is nothing but summation p going from 1 to n grad np xi xp. Similarly, grad x is nothing but summation p going from 1 to n grad xi np capital XP. So that's all. So if once we compute these two quantities, invert the second one, transpose it, multiply with the first one, we get the deformation gradient tensor. So let's do it. In this case, first thing we need the gradient of NP with respect to xi coordinates. Let us do that first, right? So let us arrange these n1, n2, n3 in a certain format, and then we'll take the gradient. Let me make it as a matrix of n1, n2, n3. Right, so this we know what it is. It is 1 minus xi1 minus xi2, xi1, xi2. Now I'm interested in the gradient. So this will so let me say gradient of uh, n1 with respect to xi. Let me call it. So this with respect to xi. So first one will be derivative with respect to xi1. Second one will be, so this will be like, so you have a -1, and with respect to xi2 it is -1. Similarly, gradient of n2 with respect to xi will be, we are dealing with 2D, so gradient has only two components. It is just 1, 0. And gradient of n3 with respect to xi will be 0, 1. So these are the gradients. Next, what to do with the gradients? We have to multiply these by the corresponding vectors. So this multiplied by x, let's not use this x1. This so now so this component, right? So now let us find the deformed grad x. So this is what this is. Uh, so this is basically a tensor. So it should have how many components? It should have. So f is 2 cross 2 in 2D, right? So this is 2 cross 2 and this is also 2 cross 2. So x will be summation shape function times this thing. So the first shape function is uh, so the first gradient is this, and the this. Okay, so one more thing. So uh, when we take a gradient here, this has got one component, this has got another component. So there will be, so this one is uh, this is a vector. This is a this means it is dou by dou xi j np of xi, and this will be the ith component. Right? So this will be the jth component, but you already have an I dependence here. So the ijth component of this will be, so the suppose you take row vectors as the components of the vector and j as the columns as the derivative. So this will be like this. You will have dou x1 by dou xi1, dou x1 by dou xi2, dou x1 by dou xi1, dou x2 by dou xi1, and dou x2 by dou xi2. Right. So this will be basically if you expand it, you will get summation xi dou np by dou capital sorry dou xi j. So this is the ijth component. So this is basically if you recall the dyadic product, it is x dyadic grad np. So it is xp dyadic grad np. So by this we mean it's actually xp dyadic. This is only the components form. So this similarly there's a dyadic product here. So by dyadic product, in terms of components, you can write it as a product of the column matrix. So the first one is 2, 3. This one multiplied by the first derivatives. What is the first derivative? It is -1, -1. Plus the second node is 2, 9, and the shape function derivative is 1, 0. And the third node is 10, 9. Sorry, what is it? Yeah, 10, sorry, let me check. It's 2, what are the nodes? Sorry, 2, 3, 3, 3, and 10, 9. So it's 2, 3, 10, 2, 3, 10, 3, and 10, 9. So this is so 2, 3, 10, 3, and 10, 9. And the third shape function derivatives are 0 and 1. Now we can find out what it is. So first one will give a -2 plus 10, 8. So it is 8. Second one will be -2, and this will give a 0 plus 10. So this is also 8. And this will be -3 plus 3, so 0. And the last one will be -3, and this will not contribute. This will give 9. So -3 plus 6. So this is this tensor in some basis, right? Now let's also compute this. What is this? So the shape function derivatives are going to be the same, -1 plus something 1 0, because shape functions do not depend on the deformation. Plus something multiplying 0 1. Now what is this? What are the coordinates? I think first one is 0 0. Second one is what is it? 3 comma 4 comma 0, and the third one is 0 3. These are the points, if you recall. Check once. Yeah, 0 comma 0, 4 comma 0, 0 comma 3. Yeah, 2 comma 3, 10 comma 3, and 10 comma 9. Now, now let us find this. First one is not going to contribute because row 1 will be 0, row 2 will be 0. In the second one, you will get first, only the first element will be there. So it is 4. And the others will be 0. And here you will get only the last element. So this will be 0, 0, 3. This will be this matrix. Now, what is the inverse transpose of this matrix? So this is what we want. So it is something transposed. But what is it before transposing? It's easy to invert, right? This is a diagonal matrix and it is 2 cross 2. So it is just, so you take the determinant, divide it by the determinant, swap this one, and do this, multiply the off diagonal entries by a -1. But for a 2 cross 2 diagonal matrix, it is just 1 by the diagonal elements. So if you, what should you multiply with this to get 1 0 0 1? It's just 1 by 4 0 0 1 by 3 transposed. But this is a symmetric matrix, so it is the same. You can drop the transpose. Now, therefore, we get an expression for the deformation gradient as, what is the first matrix? It is 8806, 8806, and 1 by 4 0 0 1 by 3. So we can compute what it is. It is 2. Then it is 8 by 3. And then it is 0. And the last one is 2. So this is the deformation gradient. So we have solved one part of the problem. So this is the deformation gradient. So the next thing we have to do is, let us find out the stresses. Let us find stresses. Okay. So to do that, we have to get to this part. So we have the, this is the expression for the Cauchy stress in terms of the left Cauchy green tensor B and the Jacobian of the deformation J. Mu and lambda are given as 3 and 2 respectively. Now, so this is a compressible neo-Hookean material. This is a compressible neo-Hookean material. So before that, let me check if the answer is right. I think it's right. Yeah, so this. Yeah, this is what we have. So we got 2, 8 by 3, 0, and 2. And that's what we have. So, so the deformation gradient is right. The next thing is to find the Jacobian of the deformation gradient. Okay, so yeah. So next, let us find the Jacobian. So this J is equal to determinant of F, and what it is? It is nothing but 4. Okay. So so one more thing, this deformation gradient is also, so this, if you see this is also known as simple shear. Okay, it's not really simple shear. Sorry. If this off diagonal entries were, sorry, if the diagonal entries were 1, then it is a simple shear. This will correspond to a simple shear. But in this case, it's not a simple shear because the diagonal entries are not 1. It's expanding, it's stretching, and there's also a shear. Anyway, so this is fine. Now, so we have found J. The next task is to just compute the stresses. So let's Let's take it there. Right? But now we have to deal with all the three components. So the full deformation gradient is as follows. The deformation is planar, so you can assume plane strain. Therefore, 0, 0, 1. So x3 coordinate is unchanged. That's what this means. Now let us compute B. B is equal to FF transpose. And in this case, it is 2, 8 by 3, 0, 0, 2, 0, 0, 0, 1. Multiplying 2, 8 by 3, 0, 0, 2, 0, 0, 0, 1. So this turns out to be so this B turns out to be multiplies. So it's 4 plus 64 by 3, 64 by 9. So it is have 4 plus 64 by 9. So it is 100 by 9. And so if this one is 100 by 9. The second entry is just, there's a 2 here. So it is 16 by 3. This will be a 0. And this will be 16 by 3 since it is symmetric. This will be 4. And this will be 0. The last one will be 0, 0, 1. So we got B. So let us find the Cauchy stress. Sigma is equal to mu by J. Mu is 3, J is 4. So it is 3 by 4. What is B? B is this thing. B minus I. So it is 100 by 9 minus 1. 16 by 3, 0. 16 by 3. 4 minus 1, 0, 0, 0, 0. This is this is mu by J, B minus A plus lambda by J. Lambda is 2, J is 4. So it is 2 by 4 logarithm of 4 plus 2 by 4 logarithm of 4 times I. I is 1, 0, 0, 0, 1, 0, 0, 0, 1. Right. Now let us find these things. So it is so 100. So this is 91 by 9. So this gets cancelled. So you get a, let us compute it in decimals. So let me just do that. So the first entry is 100 by 9 minus 1 into 3 by 4 plus natural log of 2 by natural log of 4 by 2. So it is so the first entry is 8.276. The second entry will have no contribution from the second term. It's just 16. So 3 and 3 gets cancelled. 16 by 4 is 4. So this is also a 4. Cauchy stress is symmetric. Then here 4 minus 1 is 3. 3 3s are 9. 9 by 4 plus natural log of 4 by plus 9 by 4. So this is a 2.943. Third one is 0. Again, this will have no contribution from the second term. And the last entry has no contribution from the first term, but it has one from the second term. So that is natural log of 4 by 2. So this is just 0.693. So this is the Cauchy stress. This is the Cauchy stress tensor. Again, you can check the answer. So Mm. Okay, this is approximate. They have made there's an approximate sign here, right? They said it's rounded for convenience, so it is okay. 8.276 has been rounded to 8, and 2.943 rounded to 3. But yeah, 0.693 is for whatever reason rounded to 0.8. Okay, now next task is to find the equivalent nodal forces. So, so, so up to this point, it is fine. Now recall the virtual linearized virtual work expression in the Eulerian framework. So we said it is del W internal D. Sorry, it's so D del W internal in the direction U is nothing but integral sigma. So this is basically integral uh, okay. So this is just the equivalent nodal forces. We don't let me put it in a separate page. So we have del W internal is equal to integrated over the volume sigma double colon del D integrated over that, right? So this is the virtual work done by the Cauchy stresses on the virtual rate of deformation tensor del D. Now we have discretized it. By discretizing what we did, we can also, just as we did, x is equal to summation p going from 1 to n xp np of xi. We can also discretize the virtual velocity field. So there is a virtual velocity everywhere, but we can take specific points here. And for those points, we can have a virtual velocity field del Vp. And elsewhere, we can interpolate using the shape functions. Therefore, del V is equal to summation p going from 1 to n del Vp np of xi. But what is d? D is the symmetric part of the velocity gradient. So to apply a gradient on both the sides. So we have dou vi, dou del vi, dou small xj is nothing but summation p going from 1 to n. This is the ijth component of the L. So here it is del Vp does not depend on the coordinates. You have dou by dou xj of np of xi. Again, use the chain rule. And again, there's an I coming here. This is the ith component because this is the only vector. Summation p going from 1 to n del Vp, the ith component. And here use the chain rule. You get np of xi by dou xi k, dou psi k by dou xj. So this is the spatial, just as in the last case, this is the kjth component of the inverse of the mapping from xi coordinates to x. So this is basically x, the gradient of x with respect to xi, the inverse transpose of that. And what about this? This one is, yeah, this is fine. So this is nothing but p going from 1 to n. This is del Vpi. This is the gradient of np with respect to xi. Which component? This is the kth component. And this one is del xi xi, the inverse mapping. This is the inverse mapping. And this is the kjth component. Sorry, this is the jkth component. So yeah. So dou xi k by dou xj is x inverse kj. But we have a k multiplying here. So it is x inverse transpose jk npk. So this is actually this inverse transpose jkth component. But again, what is this thing itself? This thing itself is okay. So let's do it step by step, right? So this part is fine. Up to this part, it is fine. And this I can write it as, so this del L is nothing but summation P going from 1 to n. We have xi and the gradient j. So it is, so it's del V P tensor, the gradient of the shape functions with respect to the current this one. So it is small x del small x np, right? And this is a vector, this is a vector, the product is a tensor. And one more thing, sigma double dot del d is also equal to sigma double dot del L, because sigma is symmetric. The anti-symmetric component of this velocity gradient will not contribute. So that's a simplification. We can only deal with del L. Okay. Now our task is to find this del x np. Okay. So this is nothing but dou by dou xj of np of xi. But this is nothing but dou by dou xi k of np of xi, dou xi k by dou xj. So this is again straightforward. What is this? This is so in each case. So for p equal to 1, it is this matrix we have already, right? So this we already have. So when p equal to 1, this term is -1 -1. For p equal to 2, this term is 1 0, and for p equal to 3, this term is 0 1. So this is already known. Now our task is to do this. And for that we already saw this dou xi k by dou xj is x inverse transpose the gradient with respect to xi, jkth component. And what is this? So this is nothing but, so let's find that. So for this we need del xi x, and this is nothing but summation q going from 1 to n xq nq of xi. So again, the derivative on xi applies only to the shape function, not to the constant vector. So this is basically q going from 1 to n xq and nq of this. But what is that? That is dou by dou xi of uh, it's just a vector. It's so so this is xqth ith component, and this is jth component of grad nq jth component. So this is summation q going from 1 to n xq tensor grad nq with respect to xi. And we have already computed this while computing the deformation gradient. So what it is that 4, what was it? No, it is this one, right? So it is this. The gradient of small x, this is capital X. The gradient of small x with respect to xi is this one, 8806. So grad x xi is equal to 8806. But what we want is grad xi inverse transpose. So this is, so for a 2 cross 2 matrix, so the determinant is 48. So it is 1 by 48 and something transposed. For a 2 cross 2 matrix, the inverse is swap the diagonal entries and multiply the off diagonal entries by a -1. Now you have a transpose of it. So it is 1 by 48. 6 minus 8, 0, 8. Okay. Now we have got this, and we already have this. This one is already known, right? So this we already have, and this also we have. Uh, so we can just add them up, right? So this, we have a tensor product here. So therefore, so this del L, we are going to find del L. Del L is equal to summation P going from 1 to n del Vp cross. We don't know del Vp because that is an arbitrary admissible virtual velocity field. Del Vp cross del X NP, right? So, but what is del X NP? Del X NP is this thing. And this, we have one component coming from this, which is dou NP dou XK. We have grad NP with respect to xi acting on another tensor, which is this one, this thing, right? So we have a, from the chain rule, you have one more thing. So this becomes, we have del X xi inverse transpose del xi NP. So this is a second order tensor. In this case, it is 2 cross 2. And this is a this thing. First order, this is a vector because NP is a scalar, gradient of a scalar is a vector, and this is a vector. So vector tensor vector will be a second order tensor, and that's what we have. Now we make use of this property, right? So we have sigma double dot del L. This is nothing but sigma double dot summation P going from 1 to n del Vp tensor. Let us call this tensor together as some tensor T, right? Let me just put it as T. But what is this? This is because sigma is symmetric, you can also write this as sigma. So if you take transpose on both sides, it will still be the same. Sigma P going from 1 to n, T tensor del Vp. But you know sigma. Sorry. So this is, yeah, this is fine. So it's, so but we know that sigma double dot some AB is equal to sigma acting on A tensor B. So this is basically summation P going from 1 to n del Vp. So okay, so finally what we want to find is we want to compute this vector. Okay, so we want, so this is a vector crossed with some del Vp, and this is the consistent nodal forces vector. So what is left is I have to dot product. I have to make a product of this one and this thing. So let's do that. Sigma. So let's first find out this tensor T. Okay. So and this for P equal to 1, what is the tensor? For P equal to 1, I have this tensor is clear, right? So this is 1 by 4860 minus 88. So this sigma T okay, so this will be for P equal to 1, we have grad NP as -1 -1. Therefore, what is T? T is this we just found the inverse. It is this 60 minus 88. So it is 60 minus 88. There's a 1 by 48 outside. This multiplying this one del NP, right? So this is multiplying -1 -1. So what is T? So this I can call T. For the first case, it is so it is -6 by 48, which is -1 by 8, and then we have a -8 plus 8, so it is 0. Then for P equal to 2, we have del NP is equal to 1 0. So T2 will be what? It is 1 by 48, 60 minus 8 8, and then minus 1 0, and this is 6 by 48. This is 1 by 8 0. Similarly, for P equal to 3, we have del NP is equal to 0 1, and T3 is 1 by 48, 60 minus 8 8, and 0 1. So first one will be sorry here it is there's a -8 multiplying 1 0, right? So there's a -8 here. -8 by 48 is -1 by 6, and here it is 0 6 0 and 0 1, so it is 0, and then we have a 8 by 48, which is 1 by 6. So this is T, right? So T for T in the different cases that has been cross producted with VP, and you're taking a contraction with sigma. So let's do that. So sigma, what was sigma? Sigma Yeah, so sigma T1 is what? Sigma T1 is uh, uh, so let's not worry about the last term. So it's right. So it's just with that approximation which they made, it is 8443 approximately times T1, and T1 is -1 by 8 0. So this is -1, and here it is a -1 by 2, and sigma T2 will be same 8443 multiplying -1 by 8 -1 by 6. Now this will be something. So this is -1 minus 2 by 3, so it's -5 by 3, and the first one is a second term will be -12 minus half, so it is -1. Sigma T3 will be the last one, which is 8443, 0, I think -1/6. Oh, sorry, +1/6. So this turns out to be 2/3 and 1/2. So, and this entire thing is, there's a tensor product with del VP. This is a given vector. This is arbitrary. Sorry. So this is fine. This is okay actually. This is sigma A tensor B is actually sigma ij EI tensor EJ contracted with AK BL EK tensor EL, right? So, so this is one tensor, this is another tensor. So you just contract the indices. What we get will be sigma ij AI BJ, and in this case our B is del VP. So this you can say as it is sigma transpose JI AI dot so the BJ, and this is nothing but sigma transpose, which is sigma A dot B. So this will become a dot because the resultant has to be a scalar. Now everything is fine. Whatever we computed is fine, but only thing is that it's dot with, it is a dot. It's not a this thing. And just sum them all up. Okay, so sum them all up. So del VP. Uh, yeah. So basically this is it. Now this is sigma double colon L. We have to integrate it over what? You have to integrate it over the volume. So we got these components, sigma T1, sigma T2, sigma T3, and these are these. Now integrate this entire thing over the. So what we have is del VP dot something summed over P going from 1 to 3 integral over V. Now we can take the integral inside. Therefore, we get you get del VP dot. So you have get a summation P going from 1 to 3 dot this thing, whatever is there inside dV. Now, what we have inside is the so what we have done is we have this configuration. There is some distribution of stresses inside, right? There is some distribution of stresses inside. Now this these stresses, which is internal to the element, will exert some, right? So these stresses will correspond to some equivalent nodal forces. And the work done for this element, the virtual work done by the external forces will be this equivalent forces, right? Summed over all these VP dot some external forces should be equal to the work done, the internal virtual work done over that element, right? But what is this? We are having precisely in that form, right? So we have summation del VP dotted with something. So whatever this is inside, that will be our equivalent nodal forces FP. So what we have done so far, so these components, right, these if we integrate it over the entire volume, we get the equivalent nodal forces. So for this element, you can again write the virtual work expression. So we say del W external is equal to del W internal for this element. And del W internal has got this form, summation over P going from 1 to 3, some del Vp dot something. But external virtual work, we know what it is. We have forces F1 x F1y, F1x, F2 y, F2x, and so on. We know this has got a certain form, which is summation. In every node, you're taking the dot product of the virtual velocity at that node with the FP at that node, right? T going from 1 to 3. So compare these two expressions. FP should be whatever is inside this. And what is inside that? It is precisely this one. It is integral of these things. But these are constants. Therefore, if you integrate it with mm, with the volume, and it is planar, so you can just take it as area multiplied by some thickness. So this will just come out of the thing. So what is integral dA over that element? It is just the area, right? And we saw that in the current configuration, this has 2, 3, 10, 3, and 10, 9. So base of this triangle is 8 units, and height is 6 units. Therefore, what is the area? Area is half into 8 into
24.
24 units. Therefore, area is 24 units. So our consistent nodal forces will be just all these multiplied by 24. So our first node force will be internal force, internal consistent nodal force will be, this will be minus 24, minus 12. And T2 will be, so this is, sorry, let me use a different, let me call it F1. F2 will be minus 5 by 3 into 24, which is 3, 8, minus 40, minus 24. And F3 will be 2/3 of 24 is 16, and 1/2 of 24 is 12. So these will be the consistent nodal forces. Again, we can check the answer. Yeah, minus 24, 8, 16, minus 12. Okay, that's a 0. Okay, something went wrong here. Yeah, 3, 1 is 16, 12. That's okay. 2, 1, 2, 2 are somehow wrong. And first one is okay. So we have to check what went wrong here. 8, 4, 4, 3. For 2, it is 6, 0, 1, 0. So it is 6, 1 by 48, 1, 0, 6, minus 8. Okay, something is not right here, but the procedure is fine. I think this is the procedure. I'll fix what went wrong here, but overall, this is the procedure. Go to every node, corresponding to every node, find out all these quantities. So proceed systematically. Keep applying the chain rule wherever applicable. And yeah, if you proceed it in this form, so just because I have gone a long way, I'll just summarize the procedure in one step, in one slide. So this, here is a summary of.
Hello, Naresh.
Yes, yes.
Naresh, whatever problem you solved no, now, so it will help us to solve the assignment 11 problem, no?
Yes, yes, yes. I followed the same. It's a very similar problem. Only thing is here the shape functions will be different. So this is a quadrilateral element. So you'll have 1 minus I in you'll have the
But
biquadratic shape functions.
Naresh, I want to say something about this problem. In this
Okay.
problem, there is very, very different thing from what you solved. When we will get the deformation gradient matrix, there will be
Okay.
variables there. Means
Yes, yes. This is a
that matrix.
non-homogeneous deformation.
Yeah,
So
yeah, yeah. Because means I want to say that in the deformation gradient matrix, we have to put some values regarding the xi coordinates, means eta xi coordinates. Actually,
yes,
okay.
yes, yes.
And regarding that thing, I want to ask one question. For example, we are at this step where we are solving for the del x by del xi or something, del small x by del xi, current or
Yeah,
material configuration. Okay, and
yeah.
from that we are moving towards the del capital X by del xi and del small x by del xi, and after that we have to just solve for the inverse transpose for those two
Yes.
matrices. Okay.
Yes. Yes.
Actually, when we will move towards the next step, where the grad of the shape function with respect to material and spatial configuration is there, so we have to put some
Okay.
eta and xi values there. So what should be those values? Whether these should be corresponding to nodal coordinates in these eta xi, or what should it be?
Okay, I get it. Uh, so in this problem that I just solved, everything is constant. But in general, all the quantities that we found will be a function of xi and eta. So for
Yeah, yeah.
example, if you take uh, let me just take some not that problem, but if you just take this example of uh, square going to something else, say it's skewed this way. Sorry,
Mm, yeah.
skewed this way, and say this. Let me directly say. Uh, X is some, we'll just take it as 1 plus xi plus eta plus xi eta, something like that. Multiplying some x1, x2, right? This is fine. This is this is some simple mapping, right? Now, what you said is we'll get a matrix. So, uh, this matrix will be, this will be a function of, this vector will be a function of xi and eta. So you maybe, let us just say this will be, so in every case, you will get a xi eta that's sticking on. So you'll get, say, something like 1 plus eta and 1 plus xi, right? Something like this.
Yeah.
But let me just take the actual thing. So here, suppose this is the gradient. So suppose this is the mapping. Here I will get this as x1, x2, sorry, x1, x2 will be as it is, but this will be multiplied with some, um, hmm, okay, so this will be multiplied with some, we have to differentiate it with respect to xi the first time. So first one will be 1 plus eta and 1 plus xi. I'll transpose it. So this gradient x will be x1, x2, 1 plus eta, 1 plus xi, something like this. Okay. Now this will result in a matrix that you can find out whatever x1, 1 plus eta, and so on. In the next step, you said we'll have to invert it and get that. That also we can get. So we can get x xi inverse transpose as whatever. So swap these two entries and then multiply -1. But this entire thing will still be a function of xi and eta. Okay. What was your doubt in the next step?
Yeah, actually, when this term of grad of x inverse transpose
Uh,
contains the xi and eta, so
yes.
so corresponding to these xi and eta, how will we proceed further? Because we have to put some constant values here.
No, no, not required, right? So remember, all these are functions of the position. So you have a parent element like this. It goes to some other point. Everything in the deformation gradient will be a function of xi and eta. The Jacobian will be a function of xi and eta. The deformation gradient will be a function of xi and eta. The stresses will be a function of xi and eta. So there's no simplification. You will have to carry on. Suppose you get, in this case, you will have to carry on. The inverse transpose will be, it will be minus x2 1 plus, sorry, x2 1 plus xi minus x1 1 plus eta minus x2 1 plus xi, and you will get x2 1 plus eta, something, x1 1 plus eta. So divided by the this thing, whatever determinant is. So this will be a function of xi and eta. This will also be a function of xi and eta. So there's no simplification. In general, all these depend on xi and eta. But the questions that are asked here you will not have to get to all these. So for example, okay, I refer to figure 1. It shows an element in spatial meter domain. Size of the parent element is fine. The origin at the center is there. Spatial coordinates are these. Consider a Neo-Hookean material. The Cauchy stress tensor for this material is given by this. Evaluate the following quantities. Okay.
For
Hmm.
example, first question is their ratio of volume of actual to parental
Parent
element,
element.
and
Yes.
it is directly related to the deformation gradient tensor.
Yes. Yes. So that you can get by. So you know the ratio of volumes is given by the Jacobian. So it's just
Yeah, yeah,
integral that you can
yeah.
do. So that is so Jacobian will be a function of xi and eta.
Mm-hmm.
Uh, so Jacobian of the deformation gradient will be a function of this xi and eta. Just compute it, and you can do this. Or or in this case, there's a simplification. Hmm. In this case, the simplification is your X mapping is actually identity. So your X1 is equal to xi.
Yeah.
This
This
is
I
equal to eta.
found out. Yeah, this I found out. Yeah.
So that makes it simple. So therefore,
Mm.
your F and everything, you will not need this transformation. You will not require this transformation anywhere. This will be equal to identity. So
Mm.
this will simplify a lot of things, but still, your
Yeah. Eta and xi terms are still there. Yeah.
yeah, but
Yeah.
still you will have F as a function of xi and eta. There's no
Mm.
way. You have to find the determinant in terms of, but it's all 2 cross 2 matrices, right? So it should not be difficult. It's just product. It's all 2 cross 2 matrices. Therefore, you can retain the xi and eta. You can find the ratio of volumes. It will be some right. So ratio of volume is basically the Jacobian. You can do that. Value of the bigger in plane principal stretches of the Cauchy green. Yeah, that also you can do.
Yeah, that
Once you
is
get F
also. Yeah.
smaller, you can get out of
Yeah.
plane. Yeah, this is slightly tricky, but you have to make use of something that we just discussed, right? So this is all
Mm.
planar.
Mm-hmm.
It's all planar. So this will have contribution only from the second term, right? If you start doing this, it might be hard, but this will have contribution only from the second term, and the second term only j appears in the second term, so you know what to do, right? So that's easy. So out of plane will have contribution only from the second term. The first term b will have b minus I will have uh, sigma, like b minus I will have 3 component 0. So this will not contribute. Only the second term will contribute. And you're anyway computing j already. Therefore, you can get this. You can get the value of the out of plane component. First invariant of the Cauchy stress also you can
Yeah,
do.
this I we
Yeah.
can do.
Yeah. Only thing is up to that C, up to C or U, you will have to deal with the xi and eta. But beyond that, you can do some simplification. So don't substitute
Actually,
any. Yeah.
actually, the problem is when we are finding the something like del n1 by del x, del n2 by del x, del n3 by
Yes.
del x,
Yes. Yes.
and after that we want to compute the deformation gradient tensor from this. So we from for that we have to calculate x1 1 del n by del n1 by del x plus x1 2 del n2 by del
Yes.
x, something like this. Okay.
Yes. Yes. Yes.
When we do this, so regarding the x1 x2 x3 I am very sure,
Uh,
but regarding this del n1 by del x value to
uh,
compute the f11 f12
uh.
f21 f22 all these, I am not sure actually what type of values I have to insert for this del and eta and xi. For example, I am
Okay.
computing.
So,
Hmm.
oh, are you doubtful about what N1, N2, N3 are?
No. I'm not
Uh,
doubtful about these. Even
uh,
points are also clear for me. What is x1, x2, x3? All these
yeah,
things
yeah,
I'm clear.
yeah.
The problem is, for example, I am calculating f11 component of deformation gradient matrix. Okay,
Okay,
and
okay.
for that, what I am doing, I am simply taking x11 into del n1 by del x plus x12 del n2 by del x, something like this. Okay.
Okay.
Now
Okay.
the problem is del n1 by del x is full of eta and xi. Okay.
Yes. You will have something like
Uh,
del NP by
yeah,
del
yeah, yeah.
capital
Del capital
X1.
X. Yeah.
Yes. Yes.
Yeah. So when I expand this expression, so
Yes. Yes.
basically del NP by del Xi in terms of eta and xi will be there.
Yes.
So
So
for
and
example,
yes.
yeah. Please continue.
Yeah. So in this case, del N1 with uh, you will have del N1, del X1, del
Uh,
N2,
Over
del
del
X1,
X1,
del
yes, del
N3.
N3 over del X1.
Yeah. And this, if
Yeah,
I
yeah.
remember,
Yes,
Yeah,
yes, yes.
this
This is
will
also.
yes. So this will be, I think it's just -1 minus eta, something like that. This will be -1 minus eta. This will be,
Yeah, by 4 also. Yeah, by 4 also. Yeah.
yeah, this will be 1 minus eta, and this will be, yeah, by 4, something like that.
Mm-hmm.
Yeah, you will get some things like this, but you will have to retain these values. Finally, just uh, like collect all the etas together, collect all the xi's together. That will give you some, because this is linear, right? Your shape functions are biquadratic, so the derivatives have to be linear. So ultimately, f11 will be of this form. F11 will be some a0 plus a1 xi plus a2 eta.
Yes, yes, yes.
So get it to this form, then it is just a product of, if you want j, it is, so that is some algebra, you have to do that. But since it is linear, it is less likely you will go wrong. Just keep all the constant terms separately, xi terms separately, eta terms separately, then you will get it.
Okay. But still the problem is
Hmm.
Jacobian should be something numerical value. Okay.
Yeah, the coefficients will be numerical. Coefficients will be some numerical. For example, in this case, you'll get f11 as some a0 plus a1 xi plus a2 eta. F12 will be some b0 plus b1 xi plus b2 eta. So for example, I can do one, not for that problem, but say xp is something, right? So xp, you can take it as xp of 1 as some 1, xp of 2 as some 2, xp of 3 as some -1. Sorry, it'll more, okay. This has to be some 3, and xp of 4 as some 1, right? So you can, this is some, this is like, let us just take this, right? So sorry, it is x1 of 1, x2 of 1, x3 of 1, and x4 of 1. Sorry. So this shouldn't be hard, right? So your f11, suppose this is the this is not, but suppose these are the coordinates. It will be 1 times 1 minus eta by 4 plus 2 times 1 plus eta by 4 plus 3 times 1 plus eta by 4 plus 4 times, sorry, plus 1 time 1 minus eta by 4. Right? This, it will not be hard. In fact, these shape function derivatives are correct, only the coefficients. So just take the constants together. You will get 1 by 4 plus 2 by 4 plus 3 by 4, which is 6 by 4 plus 1 by 4. You will get 7 by 4. And here it is same thing, minus 7 by 4 eta. Oh, sorry. Here it's -1 plus 2, which is plus 1. Plus 3 is 5. 5 minus 1 is 4. So -4 by 4. So that's all. In fact, f11 will not depend on eta. Sorry, it depend on xi, and f22 will not depend on eta. That you can check. Right. Yeah, that is the view. Otherwise, you can refer to the matrix form that sir has given, where you use this B matrix, right? Use B matrix multiplied by. That also you can do, but this is a 2 cross 2 problem, so you don't need to get into this. You can do it directly. So this will be
Actually,
f1. Yeah.
actually, what I am trying to say, up to this
Ah,
point, I am getting
ah,
what I have to do in this problem. But the
okay.
main thing is after this step, when I am getting F11, F12, F21, something like this,
Sorry.
are you getting?
No, I couldn't hear you. There was a connection issue. So the main thing is you said something.
Yeah. The main thing is after getting these, all the individual components of this deformation gradient matrix, the next step should be,
Tensor.
the next step, I should calculate the Jacobian, and the Jacobian should be
Yes.
something numerical value. Okay. So
No.
basically,
Jacobian also depends on xi eta. Why should Jacobian be numerical? Jacobian is of the order of f square, right? So it will be also as a function of xi eta.
but in the
Jacobian.
question, Okay.
Jacobian is a function of xi eta. So if f is a function of xi eta, so determinant of f will also be a function of xi eta. In fact, that is a property of the Q4 element. So on this element, at different points, you will have different ratio of volumes, right? Yeah, Jacobian is a function of xi eta.
No, but in the question, it is asked that ratio of volume of
In
actual
general,
element.
it could be a function of.
Uh, in the question number 3, if you read this ratio of volume of actual element to the parent element,
Parent
okay,
element. Yes, yes,
and the Jacobian is something like it is the determinant of the deformation gradient matrix.
yes,
So when this eta
yes.
or xi is present in that matrix, so can I get the numerical value from there?
Okay, that I get your point. So Jacobian relates infinitesimal volumes to infinitesimal undeformed volumes. So this is j of x1 comma x2 dv naught. But what
Yeah,
we want v by v naught. So integrate on
yeah,
both sides. So v is equal to
okay,
integral j of x1 comma x2
okay,
uh, dv naught. Dv naught is
okay,
what? It's just dx1 dx2, right?
okay.
So when you integrate it by dx1 dx2, you will get
Okay, okay. So means after getting the Jacobian
uh,
by determining the determinant of the matrix, I have to
yes.
integrate that determinant with respect to dx1 and dx2. Okay, okay,
Yeah, yeah. So
okay.
dV naught is this elemental volume. There's also some out of plane area length. You'd call it as B or something, or T or
Hmm.
whatever, out of plane thickness. So
That
this
is.
will be your volume, and
Hmm.
V naught will be integral dx1 dx2 times T. So this is
Hmm.
easy. Directly, it's the area of the square, which is 4. And here, whatever it is, you have to find out.
Hmm. Yeah. Okay, and I will put these dx1 and dx2 in terms of something like eta and xi.
No, no, no. dx1, dx2 are just d. dx1 is equal, because we saw x1 is equal to xi and x2 is equal to eta, right?
Yeah.
So dx1 is equal to d xi and dx2 is equal to d eta.
Okay, 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 okay.
So in general, you will have some transformation matrix there, but here it
Mm-hmm.
is the parent element, and parent element is 2 cross 2. So this
Mm-hmm.
integral will be just 4. V naught will be equal to 4.
Actually, what you have elaborated in this integral step, na,
Ah,
this is something new thing for me because I didn't knew this thing actually
oh,
already.
okay, okay, okay. Yeah, yeah. It is
Yeah.
known that Jacobian of the deformation gradient relates infinitesimal undeformed volumes to
Yes.
infinitesimal deformed volumes.
Yes.
But
Yes.
they are asking for the total volume of the element. So integrate it.
Yeah. 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 Yeah.
Okay.
Okay. Thank you.
Yeah, yeah, yeah. Any other doubts? Sarvesh?
Yeah, Naresh.
Yes.
Naresh, to find the nodal position of that rectangle,
Uh,
no? So
uh.
can you write down the general equation in terms of xi? You're finding the infinite element.
Oh, okay. You want me to write the equation for the
Yeah,
shape
general
function?
equation. Yes, yes.
Sorry, shape functions.
Yeah, at the nodal position we are getting no in terms of xi. For example,
Oh,
you
okay,
wrote
okay,
for the triangular element.
okay, okay, okay. So here we have the xi eta, and this is node 1, node 2,
Hmm.
node 3, and node 4. Actually, this is easier than the triangular element. So at node 1, I have n1 of so this is -1 comma -1 that you know. So n1 of -1 comma -1 is equal to 1, and n1 of 1 comma -1, n1 of 1 comma 1, n1 of -1 comma 1. All these should be equal to 0. This is the condition, right, for interpolation. At that node, it has to be 1, and at other nodes, it has to be 0. That is the condition. Now,
Okay.
now you can also look at the lines. This line is eta is equal to -1. This line is xi is equal to 1. This line is eta is equal to +1. And this line is xi is equal to -1. Now, for this, what are the opposite lines for this node? So this node, opposite lines are this one and this one. So
Hmm.
when Xi, sorry. Yeah, when xi is equal to 1 or eta is equal to 1, n1 of xi comma eta should be 0. So this is one condition. When xi is equal to 1 or eta is equal to 1, n1 of xi and eta should be 0. And we have 4 nodes. We have 4 nodes, which means we need a 4 unknowns. So it's usually like the shape functions are of the form a0 plus a1 xi plus a2 eta plus what is the next term? It is a3 xi eta. So use the Pascal's triangle. We'll have 1 uh, xi eta, xi square, xi eta, eta square. So always take the symmetric things first, right? Like this. Now, if you have 9 noded element, to go to the next level, xi cube, xi square eta, xi eta square, eta cube, uh, xi square, eta square. So if you have 9 noded elements, take this. Take symmetric terms in xi and eta because this element is symmetric in xi and eta. So in this case, we have 4 nodes. So just go to the four terms of the Pascal triangle. So a naught plus a1 xi plus a2 eta plus a3 xi eta. This is the simplest interpolation we can have, which is symmetric in xi and eta. Okay. So now for on this node, so the highest term we can have is a product of xi and eta. So now on at this node, I want the shape function for this node to be 0 at all 3 other nodes, which means the shape function for this node should be 0 along xi equal to 1 and eta equal to 1. So try this. Something like this, right? Say take n1 is equal to c1 times 1 minus xi, 1 minus eta. That will immediately satisfy these conditions, right? If you substitute xi equal to 1 or eta equal to 1, it will go to 0. So on all these 3 nodes, it will be 0. And at this node, I want it to be 1. So which means C1 into 1 minus minus 1 to 1 minus minus 1. Here xi equal to minus 1, eta equal to minus 1. This should be equal to 1. Therefore, C1 is equal to, this is 2, 1 by 4. So N1 is equal to 1 minus xi, 1 minus eta divided by 4. So similarly, if you get the form for N2, it's all symmetric. So for N2, you can guess. N2 should be, you can give it a try. N2 should be 0 when eta equal to 1 and xi equal to minus 1. So can you guess? So I want a function that is 0 when xi equal to minus 1 and eta is equal to 1. This should give 0. So
1 is 1 plus z. 1 plus z.
Yes,
Yeah.
1 plus z.
And 1 minus eta by 4.
Yeah, by 4. That's good. Then N3. N3 is here. So that should vanish when xi is minus 1 and eta is minus 1. So that will be
Both and plus will become 1 plus z and 1 minus eta. Yeah.
1 plus eta, because eta minus 1, it should vanish.
Yes.
By 4. Similarly,
By
N4
4.
will be 1 minus xi. Sorry. Yeah, when xi is 1, it should vanish.
Yeah.
1 plus eta by 4. So these are the shape functions.
Okay.
So this is this is by using the property of shape functions. There are also other ways to derive. So other ways make it fully, like, expand it fully out. Every function is say n1. We have 4 unknowns, right? So we have 4 unknowns for every shape function. And 4 equations for every shape function, and solve for all the 4 coefficients. But that is excessively lengthy. If you use the symmetry and some these properties, it will come directly. So these are the shape functions.
Okay.
Okay. Anything else?
No, Naresh. If anything is there, then I will email you. Yeah.
Yeah, you can
I
email
will
me.
try to
Yes.
solve this problem today. Yes.
Yes. Okay.
Okay.
Okay, thanks for attending.
Yeah.
I'll stop
Yes.
sharing.
Thank you.